You know that moment you click a link on a website, maybe hit send on an online order, or just refresh a page to see what's new, and almost instantly, bam, the new page loads, your order's confirmed, the feed updates. It feels instantaneous, right? Almost like, well, magic.
It really does.
But what's actually happening in those like milliseconds between your click and seeing the result?
Yeah, what's going on behind that screen?
That's the magic we're sort of pulling back the curtain on today. We're doing a deep dive into the fundamental pieces and the journey your request takes inside a web application. Our source material today gives us this really great, simple analogy to start, and then it helps us unpack the actual technical gears turning behind it all, step by step.
And our mission today is pretty straightforward. We want to demystify this whole process for you, show you the core building blocks that honestly power so much of the digital world you use every single day.
Yeah.
Think of it like getting a sneak peek at the engine room, seeing how the ship actually sails.
Perfect. Love that. And the source kicks off with this really relatable idea, thinking about it like ordering a pizza online. So let's maybe start there.
Sounds good, a tasty analogy.
Okay, so you're hungry, you want pizza, you open the app or the website. In this story, you are essentially the user.
Right? The starting point. You've got a need.
Exactly. Now imagine this pizza place is like super popular, crazy busy. People are always showing up. They can't all just mob the counter at once, right? So the shop needs a system. Our source compares this to having a front door, maybe even a smart doorman.
Okay. Like a bouncer, but polite.
Sort of. This doorman's job is to see everyone arriving and smoothly direct them to an available counter inside, so nobody waits too long outside and the counters don't get totally overwhelmed.
Makes sense.
Yeah.
Managing the flow.
Right. So once you're directed to a free spot, you talk to someone. Their job is just to listen to your order, pepperoni, extra cheese, whatever, and write it all down carefully. These are the order takers, but key point here. They take the order, but they aren't the ones actually, making the pizza in the kitchen.
Got it. Specialized roles.
Exactly. Then, after your order's taken, it doesn't just get, yelled into the kitchen chaos. No, it gets added to a structured place, like a kitchen's to-do list or maybe a whiteboard that the chefs check regularly.
Okay, so it's organized.
Yeah. This way, the chefs can just grab the next order when they're ready. It keeps things efficient. Orders don't get lost, even if the kitchen is absolutely slammed. Prevents chaos.
And finally, for the chefs to actually cook, they need the stuff, right? The ingredients, dough, sauce, cheese, and they need the instructions, the recipes. All of this is stored somewhere accessible, like a big pantry in a well-organized recipe book. This is also where they might keep track of, say, your past orders or your loyalty status. That's the ingredient storage recipe book. The pantry and the cookbook. Essential.
Okay, so that pizza analogy gives us these main roles. You, the user, the traffic director, doorman, the order taker, the task list, and the storage for everything. Now let's connect those roles to the actual technical components that power web apps and really dig into what each one does and, importantly, why it's even there.
Absolutely. Let's translate from pizza to tech. So, starting with the user, well, just like the analogy says, that's you.
The person sitting there with the browser open or tapping on the app.
Exactly. The user is the initiator. On your device could be Chrome, Firefox, Safari, or a dedicated mobile app.
Yeah.
And your action, typing a URL, clicking a button, submitting that form, that's the spark. That's the very beginning of this whole chain reaction we're tracing.
Without you, nothing happens.
Pretty much. Your interaction is step zero.
Got it. So you, the user, make a request. And our sources say the very first technical piece that request usually hits is something called the load balancer. This was our smart doorman directing the crowd.
That's right. Technically, a load balancer is a specialized piece of equipment, could be hardware or software, that sits right at the front door, strategically in front of a whole group of web servers.
Okay.
Think of it as the main entry point, the critical traffic cop for the entire application. When you have potentially, tens, hundreds, thousands, even millions of users all trying to access the site at the same time.
Which happens all the time for popular sites.
Oh, absolutely. The load balancer's core job is to intelligently distribute all those incoming requests across the pool of available web servers sitting behind it.
So it's making sure everyone doesn't try to talk to the same server at once, spreading the load, like the name suggests?
Precisely. And this is where you immediately see why it matters to your experience. Without a load balancer, or if it wasn't smart about distribution, all those requests would just hammer a single server.
And it would just lie.
It would slow down, become unresponsive, and eventually crash. You'd get that frustrating, the site can't be reached error. Nobody wants that. So by spreading the traffic, the load balancer ensures no single server gets buried. This is absolutely key for scalability, letting the application handle huge numbers of users gracefully.
Right, so the site doesn't crash during like a big sale or breaking news?
Exactly. And it's also crucial for reliability or high availability. Imagine one of the web servers behind the load balancer actually fails. Hardware dies. Software crashes. The load balancer is smart enough to detect that almost instantly. It realizes, okay, that server's not responding, and it simply stops sending any new requests to the broken one. All traffic gets routed to the healthy servers still running.
Wow, so from my perspective as the user.
You might not even notice the website just stays up and available even though a piece of the infrastructure behind the scenes actually failed.
Yeah.
It makes the whole system much more resilient.
That's huge. So it's not just about speed, it's fundamentally about the site actually being there when you need it.
It's exactly performance and availability. It's foundational for any serious web application today.
Okay, that makes a lot of sense. So the load balancer, our doorman, directs your request to one of the available servers. These servers were our order takers, and technically they're called HTTPD servers. HTTPD, what does that stand for again?
It stands for HTTP daemon. Daemon is just an old Unix term for background process.
Gotcha.
So these are the actual web servers, typically running software you might have heard of, like Apache and Jinx or Microsoft's ICER. They're the first point of contact after the load balancer has done its routing job.
Okay, so the request lands here. What's their main task? Are they making the pizza now?
Not usually the whole pizza, no. Their primary and most efficient role is serving up static content.
Static content.
Yeah, anything that's the same for pretty much every user visiting the page. Think about the basic HTML structure, the layout files. Images are a big one. CSS style sheets, those control how the page looks, the colors, the fonts. Also, JavaScript files that run in your browser to make the page interactive.
Ah, okay. The standard stuff that doesn't really change person to person.
Exactly. The HTTPD server is optimized to grab these files from disk very quickly and just send them straight back to your browser. It's like the order taker handing you a pre-printed menu. It's ready to go. Same for everyone.
Makes sense. Efficient.
Very efficient.
Yes.
But what about requests that need something specific to you? Logging into your account, seeing your shopping cart, searching for something unique, actually placing that pizza order.
Yeah, the dynamic stuff.
Right. For those kinds of requests, the HTTPD server usually acts more like a gateway or a reverse proxy. It takes the request, but then it passes it along to a separate application server. This application server is where the real custom logic lives the code, written in languages like Python, Java, PHP, Ruby, Node.js, you name it. The HTTPD server basically says, hey, application server, handle this specific request, and then it waits to get the result back before sending it on to the user.
So the HTTPD is like the front counter, handling the simple request itself, but for complex orders, it passes the ticket back to the main kitchen, the application server.
That's a great way to put it, yeah. The HTTPD handles the high volume of simple stuff and efficiently routes the complex, personalized tasks to the specialized logic running behind it. It's a necessary layer.
Fascinating division of labor. Okay, so now we're at the application server dealing with a complex request, like finalizing that pizza order. The sources mention that sometimes certain tasks related to this don't happen immediately. They might get sent off to something called a message queue, our kitchen's to-do list.
Yes, exactly. A message queue, often shortened to MQ, is basically a temporary holding area. It's a buffer for tasks or messages that don't absolutely need to be completed in real time while the user is waiting for their page to load. Think of systems like RabbitMQ, Apache Kafka, or Amazon SQS. Those are common examples.
So why would the application server do that? Why not just do the task?
Well, think about tasks that might take a little while. Sending a confirmation email, for instance. Contacting a payment gateway. Maybe processing an uploaded image or video. Updating inventory records across multiple systems. Generating a complex report.
Things that aren't instant.
Right. If the application server tried to do all of that while you were sitting there waiting for the order confirmed page, your wait time could become really long and unpredictable. So instead of making you wait, the application server does the essential bit, maybe saves your order to the database, and then it quickly writes a message describing the longer task, like send email to user X for order Y, and puts that message onto the message queue.
Ah, so it's literally like sticking the order slip onto the kitchen's spike or whiteboard instead of making the customer wait right there while the chef finds the ingredients and cooks.
Precisely. It's decoupling the immediate response from the background processing. And then separately, there are these independent programs or processes often called workers that are constantly watching this queue.
Okay.
When a worker process is free, it grabs the next message off the queue and performs the task described into. It sends the email, processes the payment, updates the inventory. This happens completely in the background, asynchronous to your initial request.
Why is that so important for me using the app?
It makes a huge difference to your experience. This asynchronous processing means the application server can respond to you much, much faster. It can immediately say, got it, your order is confirmed, or go upload received, without waiting for that email to actually hit your inbox or the payment to fully clear.
So the site feels faster and more responsive.
Massively so. It also adds resilience. What if the worker process responsible for sending emails crashes temporarily? Is the task lost?
Uh-oh.
Nope. The message describing the task is still sitting safely in the queue. When the worker restarts or another worker becomes available, it can just pick up the message and try again. The task doesn't get dropped.
That's clever. And it must help with busy times, too.
Absolutely. It provides load leveling. If suddenly thousands of people place orders at the exact same second, the application servers can quickly put all those send email tasks onto the queue. The worker processes can then work through that queue steadily at their own pace, rather than the main servers getting overwhelmed trying to send thousands of emails instantly. It smooths out the bumps.
Okay, that makes a ton of sense. Like ensuring the chefs aren't totally swamped all at once. They just work through the order board.
You got it.
All right, so we've got the traffic cop, the load balancer, the front counter folks, the HTTPD servers, and the background task managers using the to-do list, the message queue, and its workers. But where do they all get the actual information? The recipes, the ingredients, my account details, the product list.
Now we get to the heart of the data. That's the job of the databases, usually abbreviated as DBs. These are the specialized systems designed for structured storage and retrieval of all the application's persistent information.
Our ingredient storage and the all-important recipe book from the analogy.
Exactly. Databases hold everything the application needs to remember long-term. Think about user accounts and passwords, securely stored, of course, product catalogs with descriptions and prices, order histories, website content that needs updating, user preferences, session information, basically all the vital data that makes the application work and provides a personalized experience.
Common examples would be things like MySQL, PostgreSQL.
Yes, those are very common relational databases. You also have NoSQL databases like MongoDB or even specialized databases like Redis, often used for caching or quick lookups. The application server is constantly talking to the database, either reading data out, like fetching your profile when you log in, or writing new data in, like saving the details of your brand new order.
And why are these databases just completely fundamental? Like you couldn't build a modern web app without them.
Pretty much. Because without a database, the application would effectively have amnesia, severe amnesia.
Yeah, okay.
Every time you closed your browser or the server restarted, all the information about you, the products, your past interactions, it would just vanish. Poof, gone.
Right. No save cards, no user counts, no order history.
Nothing. Databases provide the crucial capability to store vast amounts of information reliably, organize it, query it efficiently, and ensure its integrity over time. They are the application's indispensable long-term memory. Without them, most web applications simply couldn't function in any meaningful way.
Okay, wow. So the database is really the bedrock holding all the specific information.
Absolutely critical.
All right, I think we've met the main players now. We have you, the user, starting everything. The load balancer, our smart doorman managing traffic, the HTTPD servers, the frontline order takers handling requests, the message queue, the kitchen's to-do list for background tasks, and the databases, the essential pantry and recipe book holding all the data.
That's the core team.
Now, let's put it all together. Let's trace the actual path of a single request, step by step, seeing how these pieces interact in sequence, following the flow described in our sources.
Let's follow that request on its journey, from your click all the way to the confirmation appearing on your screen.
Okay. Step 1. It all begins with you, the user. You initiate the action, type a URL, click a link, tap a button in your browser or app.
Click. Request launched.
Step 2. That request travels across the internet, and the first thing it typically hits at the website's end is the load balancer.
The doorman sees you arrive.
Step 3. The load balancer instantly assesses the current situation. It looks at the HTTPD servers behind it and figures out which one is currently least busy, or maybe uses some other smart rule. It then forwards your specific request to that chosen server.
Okay, directing you to counter #3.
Exactly. No getting stuck in a long queue at counter #1. Step 4. The The chosen HTTPD server, or potentially the application server it's directly connected to for some setups, receives your incoming request.
Request received by the order taker.
Step 5. Now here's where the path can diverge slightly. If your request is really simple, maybe just asking for a specific image file like logo.png or the main CSS file the HTTPD server is built for this, it's super efficient.
Yeah, it just grabs the file.
Right. It likely fetches the file directly from its local storage and sends it straight back, job done quickly.
Very fast path for static stuff.
But if you're doing something more complex, more dynamic, logging in, adding an item to your shopping cart, submitting that pizza order,
Then the HTTPD server knows it needs help from the application logic.
right. So, step 6. For these complex requests, the request gets passed to the application server. The application's code starts running. And this code very often needs to interact with the database.
Crucial step. It might need to read from the database first. For a login, it needs to check the username and password you provided against what's stored. For loading your cart, it needs to retrieve the items you previously added.
Or it might need to write to the database.
Exactly. If you're creating a new account, it needs to save your details. If you're placing that order, it needs to record the order information, what you bought, where it's going, etc., into the database tables.
Okay, database interaction happens. Now, what about those background tasks?
Right. Step 7. If this complex action also requires some follow-up work that doesn't need to hold up your immediate response, like sending that confirmation email we talked about, or maybe telling a separate inventory system about the sale, the application server doesn't wait to do it.
It uses the queue.
Yep. It quickly creates a message describing that background task. Send order confirmation, #123 to user@email.com, and places that message onto the message queue. Then it can move on with finishing your request.
Task delegated to the to-do list.
Precisely. And then, completely separately and concurrently, we have step 8. One of the worker processes that's constantly monitoring that message queue will eventually see the new message. When it has the capacity, it picks up that message.
And actually sends the email.
And actually does the work, sends the email, talks to the inventory system, whatever the task was. It might even need to interact with the database in itself as part of completing that background task. But this happens later, behind the scenes.
Got it. So, meanwhile, back on the main path, the application server has finished its core job. For my request, maybe it saved the order to the database. What happens next?
Step 9, the application server, or perhaps the HTTPD server, depending on the architecture, now generates the final response to send back to your browser. This is usually the HTML code for the next web page you need to see.
Like the order confirmed page or my updated profile page showing the changes I made.
Exactly. It packages up that result.
Step 10. This response then travels back out towards the internet. It usually passes back through the load balancer. Although the load balancer's main role is managing incoming traffic, it's still often in the return path.
Just part of the network route back.
And finally, step 11. The response arrives back at your computer, at your user browser. Your browser receives the HTML, the CSS, the JavaScript. It reads all that code.
And renders it. It draws the page on your screen.
Then you see the result. The order confirmed, message appears, the page updates, your click has completed its journey.
And what's truly amazing, as you said earlier, is how all these distinct parts, the load balancer, multiple HTTPD servers, the application server, message queue, the database, the workers often running on completely different physical or virtual machines, coordinate this entire complex dance.
Seamless.
Yeah, seamlessly. And deliver that result back to you often in just fractions of a second. Hundreds of milliseconds, sometimes less. It's a really powerful and efficient architecture when it's working well.
It really does put into perspective what's happening behind that seemingly simple instant click or tap. It's quite a journey.
It absolutely is.
So thinking about this whole flow balancer, we just traced the load balancer, the web servers, maybe the app server, the database, the queue. Why should, someone just using these apps every day, why should they care about these hidden pieces? What does it mean for them?
Well, I think understanding this stack, even at a high level like this, helps demystify the internet, demystify the apps you use constantly. It shows you that it's not just some unknowable magic box.
Right, it's systems.
There's a series of interconnected systems, each designed with a specific role working together. When a website feels incredibly fast and always available when you need it, it's often because this kind of architecture, the load balancing, the separation of concerns, the asynchronous processing is implemented well.
And when it's slow.
And when it's slow, or you get errors, or it crashes during peak times, understanding this flow gives you a better intuition about where things might be going wrong. Is the load balancer overwhelmed? Are the web servers struggling? Is the database the bottleneck? Is a background task queue getting backed up?
You start to see the potential points of failure or slowness.
Exactly.
Yeah.
It makes the digital world you navigate every single day feel a little less abstract, a bit more concrete and comprehensible. You understand the underlying structure.
It really is like having a basic map to the architecture of almost everything you do online. That's pretty powerful.
I think so.
Okay, so just to quickly recap the journey one last time, your request starts with you, the user. It hits the load balancer, the traffic cop, gets directed to an HTTPD server, the order taker,
Which might handle it directly if it's simple static content.
or pass it to an application server for complex dynamic stuff, which then likely talks to the database, the ingredient recipe storage, to read or write information.
And if needed, it sends long-running tasks off to the message queue, the to-do list, for background workers to handle later.
Then the final response comes back, through the servers, maybe the load balancer again, and finally appears on your screen.
That's the essence of the flow.
So if we connect this to the bigger picture, just thinking about it, really internalizing how these components work and interact, it feels like it gives you a pretty solid grasp of how, well, most modern online services are actually built and operate.
It absolutely does. The specific technologies might change different load balancers, different databases, different programming languages, but this fundamental pattern, this layered architecture with specialized components handling different parts of the request lifecycle, it's incredibly common. Understanding it provides a really strong foundation for comprehending the digital landscape that surrounds us all.
A powerful foundation indeed. Thank you for joining us today.